Let's recall that on the periodic table, the last electrons in all elements are organized according to the energy level and orbital that they're in. So let's focus on the orbitals specifically right now. We know that the last electrons in all the alkaline metals, alkaline earth metals, and hydrogen live in s orbitals. We know that the last electrons in the transition metals are in d orbitals, and we know that the last electrons in these non-transition metals, these semi-metals, and these other nondescript non-metals, noble gases, halogens, etc., are in p, and we've alluded to the fact that these are down here in these f orbitals, lanthanides and actinides. Don't need to worry about that as much, okay? So in the past, when an S was fully filled, we noted it as S2. When a P was fully filled, we noted it as P6. And when a D is fully filled, we noted it as D10. Turns out when F is fully filled, it's F14. But like I said, we're not going to focus on that much. What we need to look at before we understand the difference between paramagnetism and diamagnetism, really alluding to the magnetic properties or the ability for something to be drawn toward the magnetic field. If iron, for example, is paramagnetic and drawn towards a magnetic field, it doesn't mean that iron itself is a magnet. It just means that it's pulled towards a magnetic field. And it's really due to the presence of these unpaired electrons. And in order to understand whether something is unpaired, we need to look specifically at each orbital in a little bit more detail. So let's start with the s orbital. Okay. We know that the s orbital has what we call one subshell, and those two electrons can be denoted as arrows, one of them spinning in the up direction and the other spinning in the down direction. So that would be the same thing as saying S2. If we had one of them, it would be S1. And it turns out that this is the paramagnetic state, whereas this is the diamagnetic state, meaning the presence of this unpaired electron would pull it towards a magnetic field. So paramagnetic pulled towards that magnetic field. Let's go ahead and look at the D. Actually, let's not look there. Let's look at the P region. So we know that P, like we said in class, has 3 subshells, okay? Meaning it can hold a total of 6, each one holding 2. Now when we fill these, it's very important that you spread the electrons out first, okay, according to Hund's rule. So the first one goes up, second one goes up, third one goes up. Okay. Sometimes you'll put the first one here and the other one down here. That's actually, in my mind, better. They want to spread themselves out first. But as long as they're spread, spin up first. Then that fifth one is paired here and here. So that's what P6 would look like. Now, if you had something like 1, 2, 3, this would be a very, very paramagnetic state because you have 3 unpaired electrons, meaning there's going to be a lot of pull towards the magnetic field. This here would be diamagnetic. Let's look at D. D can hold 10, and we're seeing so far that those 10 are going to be distributed over half the number of subshells. So if we had something with D, there's going to be 5. According to Hund's rule, they're going to spread themselves out. Let's do it this way. 3, 4, 5. This would be very paramagnetic as we add others. D6, D7, D8, D9, and D10. Now it's diamagnetic. Okay, meaning it's not pulled towards a magnetic field. I don't really like the way that sounds. Pair, to me, the word pair, sounds a lot like they're paired. Don't like that. But I think if you remember paramagnetic as being pulled towards a magnetic field, it might be helpful. So let's do a few examples. Let's look at who has a greater propensity to be pulled towards a magnetic field, F or O. Okay. So let's do the electron configuration for F. F is 1s2, 2s2. But when we get down here to this last P portion, we're going to expand it. and it's got 5, so 1, 2, 3, 4, 5. And it's going to be this unpaired electron that's going to be responsible for its paramagnetism. Now let's look at O. O is right here, 1s2, 2s2. Notice I'm not expanding these. I could, but I'm not expanding them because we know they're already fully filled. It's only until you get to that last block. 2p, 1, 2, 3, 4. Spin up, spin up, spin up, spin down. So we notice now with O, there are 2 unpaired electrons. So because O has more unpaired electrons, it's more paramagnetic, or more pulled towards a magnetic